Hello, everybody. Thank you for joining us for the next episode of Isolation Intelligence. I'm Nathan Martin. We're going to just hold off here for another couple minutes before I introduce Dr. Taylor, and then we'll get started in about 1 or 2 minutes. There's probably about half the people that registered have signed in, so I'm just going to wait until I see that those numbers kind of settle in, and then we'll get the presentation started. So just give us another minute or so, and we'll get fired up. Thank you.
Pushy. Sweetie. Push, push. Wake.
Okay, there she's back. Good. So hey, thank you everybody for joining us today for Isolation Intelligence with Dr. Taylor. Just a little bit of housekeeping on this the webinar platform. To your right-hand side there, you'll see that there is a question bubble. If you want to ask a question, just go ahead and type your question in there. And we will do most of those questions at the end of the presentation. If you have an urgent question, there's also a raise your hand bubble. Go ahead and do that as well. And then we'll know to kind of interrupt Dr. Taylor and maybe ask the question at that time. We will, there is also going to be in the panel there handouts where the presentations that we're going to be doing today are going to be there. If they're not there by the end of the presentation, we will be putting both the slideshow and the video for this webinar onto our website within 24 hours of the presentation. So without any further ado, I guess I will introduce Dr. Taylor. Dr. Taylor is an infection control consultant at Harvard Medical. She's an ASHRAE Distinguished Lecturer and also a member of the ASHRAE Epidemic Task Group. So has lots of background in this topic, and I'll let her take it away from here. So thank you very much, Dr. Taylor.
Hey, thank you, Nathan. It's great to be here, and thank you, all of you listeners. I wish I were seeing you in person, but so these are the times for right now. But so yeah, I'm really excited to talk to you for about 30 minutes on my part around indoor air quality, health, and specifically about the values of humidification. So before we get into the meat of the studies I want to show you, I just want to tell you a little bit about why I'm here talking with you. So I'm a physician, a pediatric oncologist, and that's me on a good day in my office. And how, before we get into it again, I just want to give you a brief outline of what I'd like to talk about in the next 30 minutes. First is, even though we're all struggling with COVID-19 and social isolating and staying at home or whatever we're doing, there actually is a very profound silver lining to this, especially for those of us in the building industry. And secondly, I'd like to talk about and show you some studies on human health in the indoor environment. And thirdly, I'd like to talk about where we need to go with this. So to get started, so this is me back in medical school a couple decades ago. I decided to go on an adventure, so I went to Papua New Guinea for 4 months. You might know Papua New Guinea is around the equator. It was an amazing experience. I went to these different villages and set up clinics, traveled around in a dugout canoe. And the main hospital that I was based at was called the WEWAC General Hospital. And you can see the conditions are more rustic than we have in North America. On the right, that's me in the operating room. We're about to operate on that gentleman. I had flip-flops on. The nurse tech had no gloves. But despite these conditions, there were not very many infections that patients got from the hospital environment. And yet, in our country, in North America, going into the hospital is the third leading cause of death. That's separate from COVID-19, that's separate from why you go into the hospital. And in fact, in the US, it's probably worse than that because hospitals are reluctant to honestly publish these numbers. So I thought back about New Guinea, and I thought, why is it that in this country, going into the hospital is such a dangerous occurrence? And again, I thought back to my medical school days and my wonderful mentor, Dr. Folkman. He and I were doing research on cancer, and we were using black mice as our subjects. And one night, a lot of our mice started dying, both control mice and study mice. So I called Dr. Folkman up around 11:30 at night, and I said, something's going on. And he came to the lab, and we scrubbed the lab operating room down from top to bottom. And Dr. Folkman said, never, ever underestimate the power of the environment in clinical outcomes. So whether you're a mouse or a patient or those of us living in our homes, never underestimate the power of the environment. So thinking about the environment, let's take a quick trip through history. So quite a long time ago, we lived in these in communication with outdoor air, soil, plant material. And then as we became more sophisticated, our shelters became more protective. By the 1900s, most of us who weren't in farming were working indoors. And now in 2020, we often work in these very sophisticated, beautiful buildings with sealed windows, often non-operable windows. And our indoor environments are very comfortable. We can walk around in bare feet and a t-shirt if your boss allows it. However, along with these advances, we've also seen an increase in infectious diseases. So, maybe 2 months ago, you wouldn't have believed me, but now that we're all working the way we are and struggling with this COVID-19, it's clear that the viruses and bacteria that cause disease are becoming more and more problematic. So it's a good question, I believe, and I hope you believe, it's a good question to say, is there in fact a relationship between our building construction and management and this rise in infectious disease, allergic diseases, and autoimmune diseases? So let's take a look at that. Let's begin to answer that question. So right now, the SARS-CoV-2 virus that causes COVID-19 is a mutated coronavirus. Coronaviruses are actually incredibly common. They cause about 30% of the common cold. However, the thing about this virus and about this type of virus is that it mutates very easily and frequently. It's called an RNA virus, as opposed to us. We have DNA in our cells, but RNA viruses are known for making a lot of mistakes when they reproduce. So it's like my teenage kid writing a paper for history. And he would write, but he seemed to lack the interest in proofreading. So he would hand in lots of mistakes. That same kid is now a physician, so whatever that says. But aside from my son, RNA viruses mutate easily and rapidly. So if they encounter an environment that was previously hostile to them, such as a dry building, and there's a mutation that allows them to survive, they will replicate and continue to occupy that environment with little competition. And in addition, because it's a relatively new strain, we don't have immunological memory for this virus. So the fact that it's a new strain that can occupy a previously hostile environment and we don't have defenses has made it especially virulent. So let's take a look at humans and microbes in the built environment. So before we talk about data, I just want to show you this video. It's based on it's research-based animation. And as I'm talking and you're all breathing, droplets come out of our mouths and airways, about 100 microns in diameter. And they carry all of the normal bacteria and viruses that we have in our mouths and our upper airways. And you can see this engineer is working away. She's leaving skin particles on the desk. Those skin particles carry the normal bacteria that's on her skin, Staph aureus. You can see particles coming out of her nose, that's normal. You can see her GI tract is illuminated. We have a lot of bacteria and microbes in our GI tract. So you can tell that there's a lot of exchange between the human and the indoor environment. And furthermore, there's a lot of exchange between surfaces and the air. And that will vary depending on how the air is managed, how turbulent it is, how dry. And there'll be more or less exchange between the outdoor environment and the inside of the building, depending on openings and infiltration and things like that. So one of the most fascinating things that we are learning, and this is what actually makes your work absolutely essential to the health of the public. We now know that each of us, with all of our skin and respiratory, gastrointestinal bacteria and viruses, we're each like an ecosystem wearing clothes. And most of those organisms are very good for us. They help us survive. These are known as the microbiome of the human body. We take all of these microbes into a building, and the University of Oregon has shown that depending on how a building is used, designed, and ventilated, certain organisms are going to survive and certain ones won't. So you think about, this is a very powerful finding. It means that the indoor environment is now the primary evolutionary force for microbes, for bacteria, for viruses, for the good ones and for the pathogenic ones. So just think about that for a second. The indoor environment is now the primary evolutionary force that is shaping our survival. So are we doing things right or wrong? Are there things we could be doing better? And how do you begin to take a look at this association between human health and the indoor environment? So this is a study, now it's about 5 years old, done in the Chicago area in a hospital. So hospitals are great places to look at the impact of the building on the occupants, because we're already collecting so much data on the occupants, known as the patients. So in this study, it took place over about 13 months, and a group was looking at the movement of microbes in the hospital. So they started before the hospital was ever occupied. It's a LEED silver building, absolutely beautiful. All the rooms were single, private bathrooms. So they had taken 10 rooms and were monitoring the conditions that you see listed there. And they're measuring these things every 5 to 30 minutes. So over 13 months, they had about 8 million data points from the patient rooms. So you can see temperature, hand hygiene, pressurization, lux, CO2, humidity, traffic, room air changes, and outdoor air ventilation. So I found out about this study and said, hey, I'd like to look at patient infections in those rooms. So I had about 300, 350 patient outcomes to correlate with those factors. So we sent our data off to our MIT statistician to see if there were any correlations. So just think about that for a sec. And they came back and said, when the relative humidity in the patient rooms was low meaning a little less than 32%, the infection rate was high in those rooms. And as the relative humidity went over 40%, the patient infections went down to almost zero. So I saw this and I thought, well, you know, it's also seasonal. So these MIT statisticians aren't so smart. Should have been Harvard. No, I'm kidding. So I didn't believe this data. So we sent it off to another statistician who said, no, relative humidity is an independent variable that is associated with infection rates. And the lower the relative humidity, the higher the infection rate. This was completely opposite of my intuition. So I did another study. This one's now 6 years in the running. This is in an assisted living facility, a nursing home in New England. So for this part of the study, over 4 years, we looked at infection rates in the patients. This started before COVID-19 and is ongoing. And then we correlated the infection rate with indoor and outdoor factors. And once again, it came back showing that when the indoor relative humidity was less than 40%, especially respiratory and GI infection rates were high. And that there is something about this 40 to 60% relative humidity zone that was very protective for the patients. Now, I want to tell you, this nursing home has had no COVID-19 infections in either the staff or the patients. And about 6 miles away is another nursing home in obviously in the same area. And they've had, in the last 6 weeks, they've had about 20 deaths from COVID-19. So we're doing the other part of this study. Well, I forgot to tell you, this nursing home is now humidifying, and they're keeping their indoor environment between 40 and 60. So those are 2 studies, and here's one more. This study is in a preschool area in northern Minnesota, so probably not too far from the Odell headquarters. I'm not sure about the geography, but anyway, this study was done by the Mayo Clinic. They took a school in the wintertime. They humidified half of it to 45% and let the other half do what a building does in the winter. You bring in cold air from the outside, bring it indoors, heat it up, and if you don't add water vapor, the relative humidity is going to fall very low. And this study found that in the humidified part of the school, they're specifically looking at influenza A. In the humidified part of the school, you had less than half the same number of infectious viral particles in the air compared to the non-humidified part. Not only did they have fewer particles, infectious particles in the air, but the actual activity of the viruses, the infectivity was decreased. So that's separate from the number. And most importantly, you had many fewer children missing school from influenza. So if you're petting your dog or on your phone, whoops, I guess I took away the summary slide. So hopefully you weren't petting your dog or on your phone. So you can see in this study, there is actually an intervention in the same building. So this study begins to point to not just correlation, but actually causality, that dry air is driving higher infection rate. So let's say, okay, well, what aspects of the indoor environment are going to determine if this person is sick, what's going to determine whether or not her cough droplets are going to reach somebody else? And you can see they're the large droplets and then there's smaller ones. Up until recently, the CDC and the World Health Organization have been denying the transmission of COVID-19 virus in the smaller droplets. They've said that it's really not airborne. The fact of the matter is, I mean, the good news and the bad news is that, in fact, this virus is spread over distance through the air. And we need to really come to grips with this so that we can manage the air. One of the studies that showed that the SARS-CoV-2 virus can travel more than 1 to 2 meters is this diagram from a hospital in Wuhan. So you can see the patient bed in an ICU room, and viral RNA was found about 14 feet away, which is beyond the distance of large droplet spread. So this is just one of several studies that have made us realize that, in fact, this virus can be spread through the air for significant distances, just like the SARS-CoV-1 was. So in this process of transmission of disease, there are really 3 places you can intervene to decrease spread of the illness. You know, you can hope that somebody coming into your house doesn't spray a lot of infectious droplets through your living room. The only way you can really control that is to either lock your door or hope they have a mask on or stay away from them. Another step is decreasing viral transmission through the airborne environment or through the building. And the third step is that you can take, the third component of disease transmission is the vulnerability of other people who can become secondarily infected. So the first column, again, is a behavioral step. The second column is where indoor air management and surface hygiene is critical. And the third column, increased health and immunity, is where a vaccination would come in, or doing everything you can to stay healthy. So we now know from multiple studies that when the indoor relative humidity is less than 40%, you have greater airborne transmission. It's harder to clean surfaces because if you remember in that video, particles fall out of the air and are resuspended. And thirdly, the viruses and bacteria actually survive better in a dry environment. So I just want to check the time. Okay, a few more minutes. So just to give you an idea of the rapidity and the magnitude in droplet shrinkage, I'm talking droplets come out of my mouth about 100 microns in diameter. And in a dry, low relative humidity space, those droplets shrink very rapidly. And by the time they reach half a micron in diameter, they're known as a droplet nuclei. They can float through your building and they've been recovered hours and days later. And with many, many organisms, a droplet carrying the infectious virus or bacteria will still be infectious days later. So this graph shows, this is really fascinating, showing that with low relative humidity on the x-axis, the infectivity of influenza A remains high until you get to 40% relative humidity. For some reason we don't fully understand. At 40% RH, the infectivity of this virus plummets. And for many viruses, it comes back around 60%, but there's this sweet spot, 40 to 60%, where human health is optimized and the infectivity of most bad respiratory viruses and many bacteria is diminished. And so that was influenza A. If you look at the coronavirus, on the top black line, you have 20% RH and comfortable temperatures. And you can see that the virus stays active. Then the green line shows 80% RH. So that's above that sweet spot. And you can see there's some inactivation. But at 50% RH, you have maximal inactivation of the infectivity of this inactivation of the virus. So that's the virus. Let's just talk for a minute about human beings and water vapor. We are not designed to live in low RH. If we were a droplet, we can shrink and travel around. If we're a plant, we can wilt. But as human beings, we have a skeleton. So what we do is we crack and our mucous membranes dry up. So let's specifically focus on the respiratory tract since we're dealing with respiratory disease right now. What happens to the human respiratory tract in low relative humidity? So this Dr. Iwasaki at Yale published this study last May, just about a year ago. And she used genetically engineered mice that have the same immune response as humans to influenza A. And she said, why is it that we get the flu in the winter? Why is it in low relative humidity situations do we get more sick than we do in a moderate relative humidity environment? And what her lab found was that all of the natural protective steps of our immune system are impaired in dry air. So in your respiratory tract, this layer of mucus that lines your nose, your throat, all the way down into your lungs becomes slightly dried and more viscous. These little hairs called cilia cannot protect our lungs from particle deposition. And furthermore, downstream protective mechanisms of our immune system are actually impaired in dry air. And at 50%, those steps are optimized. You might recognize this. This is the Sterling-Avondale graph from 1985. We've known for quite a while that this 40 to 60% sweet spot exists, where infections are diminished and human health is optimized. And if you take all of the data with the new testing techniques, with computer data analysis, we're still seeing this sweet spot, 40 to 60%, that's very protective to humans. So what do? We must move forward and design and manage our buildings and our HVAC equipment to support this relative humidity zone. You know, why do we have buildings? Yes, they protect us. Yes, we want them to be energy efficient and we want them to be beautiful. But we now need to recognize the role of the building in occupant health. So when I talk about the sweet spot, I mean, not the sweet spot, but the silver lining of this pandemic, it actually is forcing us to look at the importance of the indoor environment in protecting health. And humidity, low humidity has reared its ugly head as being a very powerful driver of disease. Conversely, with humidification, you can interrupt this process, this transmission. So maintaining the relative humidity between 40 and 60 is the only strategy that both cleans the air and decreases surface recontamination. And based on the research of Dr. Iwasaki, it actually supports your immune system. So it's a very holistic and effective approach. So again, this is just to show you it decreases transmission and supports our immune system. You can have this presentation and go through this a little more slowly. But my belief is that as this trend of infectious diseases has occurred, it's to some degree due to the fact that we're sealing our buildings, we're separating ourselves from the beneficial aspects of the outdoor environment, and we've dried out our indoor air. And it's not good for people. There's enough research that we actually have a petition to the World Health Organization to reestablish a minimum relative humidity level in buildings. So if you remember this, it's www.40to60rh.com. You can sign this petition. I'd be very appreciative. So thank you. And now I'm going to turn it back to Nathan. That's my buddy Luigi, who's about 4 feet away. And thank you very much. You can have this presentation And there is a bibliography at the end, which you can use to look. Oh, here it is. Whoops, there it is. So thank you. Back to Nathan.
Okay, thank you very much, Stephanie. That was very enlightening. Could you confirm for me that you can see my piece of the presentation here?
I think I might still. I cannot.
I have it, Nathan. It's Jerry here.
Yes.
I can
I
see
can.
You can see it? Okay, great, great. So a nice segue from Stephanie's presentation to, I've just got about 10 or 15 slides here I wanted to go over with the group to show you how Odell Associates and Condair can work with you to support delivering 40 to 60% RH within your buildings. I guess first off, there are two main ways that we currently can humidify. There's isothermal, which is what most of you have lots of experience with. That's a very traditional means of humidification, where you're effectively boiling water and putting that steam into the air, whether that be in space or whether that be through the duct system. More prevalent in the last 5 years has been the insurgence of adiabatic humidification, which includes a number of different technologies from evaporative to high pressure nozzles. Often it's for large projects, but also available for smaller projects. And the reason it's become more prevalent in the more recent years, I believe, is that it addresses maintenance and also addresses energy and can support some energy efficiency measures within your building. So just kind of give you a bit of a 10,000-foot view of Condair and what they're able to deliver on the steam generation side. Is they do have the full list of products, everything from the electrode steam, which is basically what I always refer to as the Sherpa of Condair. It was the original product that Condair brought to market and has built a very strong offering in humidification off the back of that product. And then there are other electric. We also have electric element, gas, and then live steam humidification solutions available. Just a little bit more on electrode. As I said, it's the original humidifier from Condair. It's got very good controllability, very easy maintenance from removal of a cylinder and replacement with basically making your humidifier like new. That said, some applications where you have difficult water conditions, it may not be a suitable solution. So a number of years ago, Condair launched the RS, and the RS is a heating element style humidifier. The heating element with this one is has no dependency on the water conditions. In fact, we can use everything from deionized water to RO water and to potable water. It lends itself very well to high precision with SSR controllability as an option. And it also lends itself very well to really, really tough water conditions. For those of you that live in Waterloo, you'll be all too familiar with those conditions. And with having a scale collection bucket and some other features with a scale solution that helps to maintain the length and longevity of the operation of this unit. They also have for steam generation the GS gas units. The gas units are there's 3 different models available in the gas unit, from a mid temperature, which is about 84% efficient, all the way up to the condensing model, which is about 93% efficient. Had a lot of success with the condensing model and very, very good product. The Nice thing about the condensing is you can get away with CPVC pipe venting, which is really, really easy for installation for any contractors out there. Also available in 50 pounds per hour now, as low as 50 pounds per hour, which is nice. Even at 50 pounds per hour, the payback for going to a gas unit over the electrode, the equivalent electrode, is about 2 to 3 years. So some good opportunities there. I just wanted to also speak, obviously, that was the live steam, isn't that live steam, sorry, the isothermal side of the business. Condair also has a very, very strong offering on the adiabatic side, both in duct and direct room applications. With these systems, often water condition is important, so Condair can right size or match an RO system for any of these systems as well. I just wanted to maybe highlight a couple of these systems to give you an idea of what's available to you. Going from left to right, we have the ME evaporative style humidifier. It's a very compact humidifier. It also delivers good humidification, but not tight control. So if you're looking at just maintaining plus or minus, say, 10% RH in your space, it's a good fit. It also comes with the benefit of delivering cooling, just like any of the other adiabatic solutions in this offering. The next solution would be the high pressure nozzles. They can be put in a duct system. We actually have a nice project profile available on our website for a project we did in downtown Hamilton at 25 Main Street, where we were able to use one pump module and serve 2 air handling units with a single system. You can get very good modulation out of this unit, and obviously hygiene is important as well, so it's good for that as well. And then there's the hybrid system. The hybrid system kind of marries both evaporative and the high pressure nozzle systems in duct, where we have nozzles that operate at a lower pressure, around 100 psi, versus the 1000 psi that the high pressure works at. And then there's an evaporative pad that is downstream. I'm actually going to let Jerry take over on the next seminar. Next slide here, and maybe just explain the DL a little bit further to them, Jerry.
Okay, thank you. And Nathan, you can hear me?
Yep, I can.
Okay, good. So ladies and gentlemen, thank you for your time. My name is Jerry O'Neill. I'm Regional Sales Manager for Condair. And what we have is a schematic showing you the dual or the hybrid unit. And as Nathan mentioned, it's an HVAC application. It's in duct. It takes up very little space, but it answers really or overcomes some of the issues that people have with humidifiers. And let's be honest, our humidifiers are known as being expensive to operate, and they are dirty and require a lot of maintenance if you're using potable water with scale. So with this system, this was developed specifically for clean applications, healthcare, biosciences, long-term care homes, etc. And it can be very low operating cost and very efficient. So if we were looking at this moving from left to right, the airflow would be coming from your left to the right. That section right there between those 2 banks, we have on the left a bank of nozzles, and then we have a media pad. It's made of ceramic. There is really no maintenance to do with any of that. It's only a 2-foot section, as Nathan is showing there. And but in all, for door access and other things, we would require an extra foot on each side, so about 4 feet. So as we're going and looking at the filter, we would bring in our potable water. We'd filter that water to remove the chlorine. From there, we would go into the softener. We would remove the scale, the calcium, and replace that with sodium. From there, we would go into our RO system, and we don't have a pump on there, but you will see the UV lighting. You'll see the control board. There is a storage tank that you can't see in the back there. And then there, of course, there's the RO membranes. And for those of you not familiar, not to be pedestrian, but what a reverse osmosis water system is that we pressurize potable water and we send it through a very tightly wound bank of filters, if you will, almost like coffee filters that are wound very tight. The water, the good things in the water are allowed to pass through these filters. Up to about 96% of all the bad things in the water are filtered out so that our water is pure. We can go to the next step after RO is deionized water, where we're polishing that water to zero conductivity and zero hardness. RO water is generally defined as about 5 to 15 grains of, 5 to 15 microsiemens and 0 grains of hardness. So from there, you can see we have a little hydraulic unit there. I'll refer back to that in a second. The water is then under low pressure, as Nathan mentioned, anywhere from about 42 to 90 PSI. So it's a very benign water spray. We have up to 31 stages of modulation, and we have the manifold and the nozzles that we put together. All the modulation is done by us. And then we have atomizing in that area. So we're getting instant humidification, very responsive. Instead of all that water not going to drain because we're asking to do a lot in that section, that's the whole purpose of adiabatic technology. We are converting that liquid to a gas using the energy in the air as opposed to a utility. And 2 feet is not enough time for that water to be absorbed. So under normal circumstances with different equipment, a lot of that water would go to drain. But in this case, with the hybrid technology, the water sits, it doesn't saturate, it actually sits in these thousands of pockets of holes in the ceramic media, and then it becomes evaporative. Just some design criteria. We don't want to exceed about more than 690 feet per minute. There's no aerosols. There's nothing that gets past the ceramic media. But we're very obsessed with hygiene. So we know about CSA and other things in hospitals, and we respect that. But we're obsessed with hygiene. So that's why we use RO water and or even DI. But we have a little thing within the hydraulic unit, and I believe it's on the next slide, Nathan, if you could go to that. No, it's not. Sorry, within that section there where the red dot is, there's a little tank right there. That's the only consumable or the only repurchase anybody has to make. And that tank contains pure silver. And what we do is we dose the water with teeny amount of silver so that that area, that 2-foot section becomes almost like a quarantined or a hygienic zone. Silver is a natural killer of bacteria on contact. So that is one thing. The other thing is that unlike a lot of RO people that operate RO, the tendency is to make thousands of gallons or hundreds and hundreds of gallons of RO water and store it in a clear tank. It's open to atmosphere as required by code. Our tank is very small. It's black. It can't be affected by sunlight. And our opening is a 0.2 micron HEPA filter. Water, when you alter or change its character, wants to get back to stable. So it will draw carbons from the air. It will draw minerals from copper, brass. It will even draw minerals from your body. So because of this and because of the hygiene, we're the only humidification company in the world that has what's called the Fresenius Institute rating for hygiene. It's a liquid, if you will, or hygiene certification. And to give you some examples of where it's used in other places, you cannot operate kidney dialysis equipment without being Fresenius Institute rated. So that is really the message or one of the highlights of the products that we'd like to talk to today. But of course, please contact Nathan and Odell for anything else or anything more specific. And with that, I'll turn it back to you, Nathan.
Thank you, Jerry. So just another couple slides here to talk about the systems. So with adiabatic, it lends itself really well to in-space humidification. Obviously, one of the major advantages to in-space humidification is the humidification piece is 100% efficient as far as getting the moisture into the air. And it's also very good for large loads. So we see a lot of in-space humidification being used in areas where you have large industrial plants, printing presses, car plants, lots of larger plants. But the nice thing is because of the flexibility of these solutions, you also can extend those systems into the office spaces that are serving the larger facility. So if you look, there's the flex dual bar kind of distribution system. You'd need pretty good ceiling heights for that solution of between 25 and 30-foot ceiling heights to make that a viable solution, make sure the plume fully absorbs in the air. Then you have the Princess, and which is another solution for, and it actually has a little fan assist that allows us to drop that ceiling height requirement to around 18 feet. But then when you go into office spaces, often you don't have that kind of ceiling height to work with. But what we can do is you can use these Unos or these Solos, and they actually are capable of being used in spaces that are as low as 8-foot ceilings. So that makes the ML system, high pressure system, and in space very configurable to many different applications. And again, it also is available with the RO system that is part of Condair's package. So moving on to the next slide, I thought I would put in a little bit of just more of a teaser than anything else on energy efficiency. And so as you can see, Condair has a very, very broad and comprehensive line of humidification solutions to meet pretty much any need. And obviously, energy efficiency is also a part of the equation. And just from a quick view of a very quick energy analysis, if you look at a 1,000 pound per hour solution, 1,000 pound per hour load, the hourly operation cost for an electric humidifier is $35. Then we step down to a live steam, and it's $20 per hour. And then the next step is $9 per hour for a gas unit. And if you look at adiabatic, it's 2 cents. It costs 2 cents to deliver 1,000 pounds per hour of humidity to a space over an hour. Pretty significant drop. Of course, this looks at humidification and delivering humidity to the space. There is heating required in some instances, so that levels the playing field a tiny bit, but not nearly to the effect that the adiabatic doesn't deliver a very strong energy efficiency message. It also creates an expanded number of hours in economizer mode for most buildings, which is another solution that helps us save some energy. So that's kind of the scope of what we want to talk about today. The big takeaways for me on today's presentation, obviously, is Dr. Taylor delivered an amazing presentation on the importance of humidification as a primary driver of indoor air quality. That designs should be looking to maintain between 40 and 60% RH in our spaces. Condair is a full line supplier of all available technologies in humidification. And again, if you need any support at all in humidification, Odell Associates is here and ready. All of the sales team here at Odell is very well educated and versed in the application of humidification and supporting you in those requirements. So that's those are the big takeaways. Maybe what I'll do now is take a couple minutes here and see if there's any questions, and we'll go through some questions and answers. Stephanie, you're still there?
I'm still here.
Perfect.
Somewhere. There I am.
Yep. I've got the questions here, and I'll just go through them, and we'll see if we can get them answered. So I'm trying to get them up here. Okay, so let's go here. Okay, here's a question. Does atmospheric pressure play a role with humidity in the indoor environment along with body inflammation?
Is that for me?
I, I think it's for one of us. And I'm not sure how to answer that. Does atmospheric pressure play a role with the humidity in the indoor environment along with body inflammation? Not
So
sure how.
when I've looked at, if I'm understanding this question correctly, I think, the atmospheric pressure at sea level is different from the Rocky Mountains. So I incorporate those differences in my definition of absolute and relative humidity. So if you're asking something that's outside of that level of sophistication, I don't know about atmospheric pressure. I do know that outdoor absolute humidity has often been said to be the main driver of seasonal respiratory viruses. But in fact, it's when you bring that amount of humidity indoors, heat the air up, and the relative humidity plummets. So again, I don't know if that's your question. And then if a person already has an inflammatory process going on in their body, it doesn't change their need for a given amount of water vapor or humidity. And in fact, when you say the word inflammation, I think of autoimmune disorders, I think of chronic inflammatory disorders. And we now know that many of those ongoing inflammatory diseases are related to particles in the air. And that's another factor that's improved by this mid-range humidity. So again, I'm taking a stab at that question, not really knowing if I've understood it correctly.
Yeah, I think that's a good answer. We can always go offline with the person who's asked that question and maybe get some more detail on what specifically the question was related to. Okay, so next question is, does the position, I think this one would be for me more than anybody else, does the position of supply and return air distribution vents support/hinder the spread of infectious air droplets throughout a space? I will put it over to you, Stephanie, if you have any specific comments, but I certainly have some comments I can make on that.
So why don't you take that one, Nathan?
Okay. Yeah, so return, I would say yes. The answer to that would be yes. You do want to ensure when you're placing supply and return grills that you're generating air currents within the space to keep, specifically in a hospital, especially in a hospital environment, keeping the cleaner supply air at the face of a patient or up top of the bed, as opposed to and keeping the return air further away from where people are breathing. So the answer is yes, and there should be caution made in where you put supply and return air. But I would say that supply air is likely more important than return air. Because it is my analogy is always, it's very difficult to suck out a match. So you don't, return air is not as critical as supply air, but maybe Dr. Taylor, if you have anything to add to that.
I'm not sure what you mean by mash.
A match, like a flame.
Oh, a match.
A match, sorry, yeah.
So I think in a setting with say a vulnerable patient, I wouldn't want the return air to be near my breathing zone. Especially,
exactly, I agree, yeah.
My son, who's an ER physician, is working in a hastily constructed COVID-19 zone in a big hospital in Boston. He was distressed because the whole physician-patient area is one room, one big room, about 24 beds. It's under negative pressure, and he said that the exhaust vents are right over the physician documentation station, which sounds terrible to me.
Yeah, I wouldn't recommend that either. So next question. I assume the studies mentioned were performed at room temperature. Does temperature have an effect? For example, in a food facility where workers may be working in an environment that is 50 degrees Fahrenheit, is the optimal RH range still the same?
So the optimal relative humidity range is the same. And as you know, relative humidity takes into account temperature. we just had somebody asking about meat preparation facilities and saying that it's very hard to keep the relative humidity in that range because it's so cool. But anyway, so relative humidity, as you know, incorporates the temperature. So the 40 to 60% is a critical sweet spot there.
What could be an optimal, this one is probably likely for myself, and maybe if Jerry wants to pipe in here, what could be an optimal RH to avoid static charge in the air? So Jerry, do you want to take that one?
Yeah, that's a good question, Nathan. I don't have the chart on me right now, and thank goodness there's no amps but behind it. But a typical, and we're talking about static now, but a typical person walking across the carpet generates something like 25,000 volts at low humidity. I will have to look out that chart and get it to you, Nathan, and then I can't answer that right now because I don't know the answer and I don't want to misspeak. So I'll get that chart, I'll forward it to you, and then you can forward it on to the questioner.
Yeah.
Did you have any comments?
Yeah, I would suggest static is one thing, and obviously health is another. And generally, if there's people in the space, and 40% would be kind of the minimum number that I'd want to see in a space, and that is effective at managing static charge. So, but yeah, if you could get us the chart, Jerry, I'd very much like that, and I can get that off to the guy who's asked that question.
Yeah, definitely. And I think too, the other thing, it's not only static in the wintertime, as we all know, we've all touched our computer or our desk or our lamp or something, but it's also the dryness in the skin, the eyes, all the things that Dr. Taylor talks about too. So it's still 40% at the end of the day.
Yeah. Is there a quick manual for selecting humidifiers to patient care areas and others in hospitals? The quickest manual would be to give Odell a call, and we'll support you through, because we do have to look at a number of criteria. What size is your air handling system? What's the load going to be? What sort of room are you delivering the air to? So there are some questions that need to be asked. So as far as a quick manual, not really. If you want kind of a rule of thumb, lower lower humidity requirements, like less than 30 pounds per hour. We're usually looking at an electric humidifier with some sort of in duct distribution or in space. If you're above that, we're usually looking at a gas between 30 to 100, 200 pounds per hour. We're looking at a gas style humidifier. And then above that yet, we're looking at some sort of evaporative style humidification system. So, but we do need to be on that. We do need to be cognizant of CSA requirements for adiabatic in hospital settings. Okay, so are adiabatic humidification systems more susceptible to water/vapor-borne bacteria, such as Legionella or similar? If so, what must one look for in systems or in maintenance programs to minimize these kinds of risks? So I'll speak to that, and Jerry, you may want to pipe in with any additional comments here.
Sure, absolutely. Go ahead, Nathan.
So I would say they're no more susceptible as long as the water conditioning is maintained with RO, as well as no standing water is let to sit in an air handler for any length of time, or standing water sit inside piping. All of the Condair solutions do have hygiene flushes and hygiene requirements to make sure that those things don't happen. There's also end of season shutdown requirements to make sure that water doesn't sit for extended periods of time without being circulated. So there isn't any I wouldn't say that adiabatic is any more or less susceptible to bacteria and water vapor-borne bacteria. So Jerry, would you have any commentary on that?
Yeah, I agree. There is a certain comfort level in boiling. That's why we do boil water advisories. Water, we know that when we boil water, we're killing off bacteria. But what we do at Condair, it all begins with the water. The equipment itself is benign. If we were to install any of our adiabatic equipment inside an HVAC system, and that's all we did and came back 100 years, it would be all deformed and weeds growing all over it. But there wouldn't be any problem with it. It's when we add water. And you're right, Nathan, all the things you said. There's no standing water. We use UV lights. We have recirculation. We have no call humidity for 12 hours. We do full tank dumps. And we also check and we make sure on the velocity that no aerosols get past our wet stainless steel drain line section. So you're correct. So we do wear our suspenders and our belt. We take hygiene very seriously.
Thank you. Okay, so Dr. Taylor, here's one for you. Why is the behavior of viruses changed to more inactive between 40 and 60% RH? For example, do the water particles make the viruses drop to the floor quicker?
So, I mean, that's an amazing question. And the phenomena of the infectivity being decreased between 40 and 60% is separate from the decreased number of particles in the air. So yes, there are fewer particles in the air because you know, they're hygroscopic, they enlarge and drop down. But separate from that is this finding that bacteria and viruses, the pathogenic ones, are often less infective in that 40 to 60% range. And we don't know why. We don't know if it's a change in size and therefore a change in the salt and pH of the interior of the droplet or bacterial cell. We don't know if it's a membrane communicating with the nucleus, with the genetic material. But whoever asked that, if you want to figure it out with me, we'll probably go to Stockholm together and get the Nobel Prize, because that's a really active question.
That is a good question. So a couple RH humidity style questions here. Do you have any data of what are RH levels usually maintained in average residential buildings? I don't know if you've got any specific data, but I have some, typically you'll see in Canada, not in Canada, but Ontario, if you don't humidify, humidity levels in a residence would be anywhere from 15 to 20% in the middle of winter. And that's with people showering and bathing regularly. So that's kind of the numbers I've seen when I've done my tours, and that's more anecdotal. I would say that I don't have any studies, but I've been in enough houses and provided humidification to enough residential spaces that those are kind of the numbers we see at the start. So, Dr. Taylor, you see anything else?
No, I mean, most buildings don't actually monitor indoor relative humidity unless you have a, you know, data server or a famous piano or old books or a piano, or if the NIH research labs where the animals are housed, they're going to be between 45 and 55. But for us mere mortals, it's not something that's usually provided, unfortunately.
Right. I know my house is 40%, so because I do humidify my house, so that's good. Yeah. So question here, I guess, was more on my my energy analysis, but it was what type of facility would have 1,000 pounds per hour load? Are we talking a hospital or a home? Certainly not a home. A home is going to be less than 10 pounds per hour for the most of us. Rarely see them over that. It's usually between 3, 4, 5 pounds per hour for residents. 1,000 pounds per hour is generally a larger industrial facility. It can be a hospital as well, depending on the size of the hospital. But 1,000 pounds per hour is going to be a large commercial building or a large industrial facility.
Nathan, just to jump in, our largest facility in North America is 26,000 pounds per hour, and it's a manufacturer of the turbine windmill blades. They're 75 foot long, and they use the direct room system. And they're getting 3 or 4 different benefits of humidification. They have static issues. Talking about static again, they hand sand all the fiberglass blades, and you can imagine fiberglass. So the system actually adds weight and brings all the dust down below operating level, and they get cooling also. Our largest job in the world for humidification is 50,000 pounds per hour, and it's an outdoor mosque in Medina, Saudi Arabia, comfort cooling.
Another question here, what percentage of supply air could be outdoor air or fresh air in hospitals, 10% or more? The answer to that is it depends. Administrative areas could be as low as 10 to 15% outside air, whereas other like negative pressure rooms or other rooms within the facility could be 100% outside air. So it's really dependent on how they're using that space and what it's being used for patient care. Dr. Taylor can probably be more specific on different rooms, but it's very variable depending on the application of the space.
Well, so, and also the COVID-19 pandemic has changed some of the regulations around outdoor air. For example, the European document, REVA, I believe is the acronym, says that air should be primarily all outdoor. It should all be from the outdoor space and turn off recirculation. That's been modified, and ASHRAE does not support that because we realize there needs to be a balance between outdoor air and maintaining indoor humidity and temperatures without using an exorbitant amount of energy. So I think the best thing to do is to go on the ASHRAE Epidemic Task Force website or to look at some recent codes around outdoor air fractions. But whatever you do, you need to maintain your indoor humidity. It's the best thing you can do.
Yep. Yeah, I've seen, since COVID-19, I've seen a number of studies talking about the connection between PM10 and PM2.5 and the associated level of risk, and how they're seeing that can be carriers of virus. I don't think anything's been conclusive yet, but
Yeah,
there's certainly...
There's a good paper that came out of the Harvard School of Public Health showing that the PM2.5 size particles are high particle levels are very much associated with an increased risk factor for COVID-19 infection. But I called the main author of that paper and said, what about relative humidity? And he said, yeah, well, when the humidity is low, the particle count is high. So
yeah.
Related,
yeah.
but humidification manages both the particles and the virus.
Cool. I think there's only one more question left here. How do you keep RH 40 to 60% in hospital bedrooms and laboratories? I can take that. We need to look at the sources of ventilation air or outside air that are coming into the space, which would be the amount of dehumidification happening, and which brings in low absolute humidity, and be able to offset that by delivering either steam or adiabatic humidification into the ducts air handling system to deliver that steam to the space. So maintaining the RH is simply by putting humidifiers into the air handling system to put more moisture back into the air after the outside air is brought in the middle of winter. So that's on the humidification side. There are going to be areas where you might find dehumidification when you get above 60% in the middle of summer, but generally hospitals are cooled, so that kind of takes care of itself, just by virtue of the cooling side of things. So
Nathan, if I could add something, the trend, some of you may know, I work both in the US and Canada. In the US, not COVID related, these were jobs that have started in the last year or so, but the trend that we're seeing in US hospitals, of course, besides the improvement in architecture, Dr. Taylor mentioned the lead hospital in Illinois. But we know from an architecture standpoint now that hospitals, the days of wards are gone. You're not seeing 2, 4, 6, 8, 12 patients in a big room anymore. It's one person, one room. But the other trend that we're seeing, at least with a few jobs now with greenfield hospitals, is that they're being designed with humidification from the basement to the top floor. They're no longer isolating or doing the ICU, the burn unit, and the OR. They're doing the whole.
Questions? Once again, everybody, thank you very much. Jerry, thanks very much for your help on the responses.
Thank you, Nathan.
Dr. Taylor, Stephanie, thank you again. Very enlightening, excellent presentation. I appreciate listening to you every time that you present. And thank you for doing this for Odell. And thank you to all the attendees for spending time with us today and learning about humidification and how we can support you in delivering superior indoor air quality at either your facility or within the designs that you're working on today. So again, this presentation will be available on our website within 24 hours, the slides as well as the video recording. So thanks again, and I hope everybody has a wonderful